You find that if you hang a 12.5 kilogram weight from a vertical spring, it stretches 3.75 centimeter. So we have a spring. Normally, this is its natural length up to this point. And then if we hang some mass into the other ends of the spring, it will stretch out. So we can see that there's a change in the length of the spring. And in this case, this mass is 12.5 kilogram, and this delta x here, the change in the length of the spring is 3.75 centimeter. They ask for what is the force constant of this spring in Newton per meter. So force constant to do with spring, that we need to review what mentioned in Hooke's law, where he find that the F elastic to restore a spring to its initial shape would be proportional to the change in the length of the spring. It should be a negative because it will be like against the change. So if it's stretched out, then the tendency of the force is that to make it return to the initial shape. So there's a minus, a negative side here to indicate that. And K here is just a constant. So it depends on the stiffness of the spring that the K can have different value. The greater the K, the greater the F elastic, and that will represent indicate for the stiffness of the spring. In this case, they ask for it. So how can we find it? And okay, so why don't we start from the free body diagram? What is a free body diagram? A free body diagram is a diagram that free a body, which means that no body shown, and which is focused on the forces, the reason, the cause of the change in motion, which is the acceleration. So because we can like investigate the motion of the object by analyzing the forces acting on it. That's the purpose of these problems in the chapter of forces. So back to the point. In order to draw a free body diagram, we would need to identify which body we are investigating here, how many forces that acting on the body, and then we need to identify each force based on the interaction between which object and which object, its direction, and also its magnitude. So in this case, we have the objects here that can help us to identify the spring will be this one, the mass here. So let's see how many forces acting on it. It stays at rest, it stays still after the stretching, and then there's only gravity, right? Only weight from the earth acting on it downward, and the magnitude should always be like mg, right? M is the mass of the object and g is the gravitational field or gravitational acceleration, which equals to like 9.81 meter per second square. So then we can identify the weight. The second force here that have to do with the elastic spring, that could be the elastic force that have to restore the shape of the spring and also like act on the object. So this one we need to follow the Hooke's law. That's why we got it like K delta X with the minus here. So here we see that the block stays still. So like apply the Newton's second law, F net equal to 0. We have just these two forces should cancel each other. And if they cancel each other, then they should be equals in magnitude, in the length, in the strength. So then they as strong as each other and points in opposite direction, then it can make it to be 0. So then this one just left with K delta X, mg. We know M, this one. We know G, this one. We know delta X, this one. Can we find a K? Yes, for sure. So then we can just set solve for K and then just do the math, plug in the values. This is the force constant. So this is kind of like some constant. Then it can be like the spring need to be strong enough, then it can like hang this heavy mass, 12.5 kilogram. For the second question, they ask, how much mass should you hang from the spring so it will stretch by 8.13 centimeter from its original unstretched length? So actually, this is not too complicated to solve. It's just like the same method, just instead of giving us everything and asking for K, now for this question, they change the mass, right? They change the mass. So then they can have a different change in the length of the spring, delta x2, m2. And now just like cut the same sum for m2. That's what they're asking for, how much mass. Then we have the mass is like 27.1 kilograms. So we can see that the bigger the mass, the heavier, the more the stretch. And here just pay attention that you need to convert everything into the SI units, so centimeter into meter, and then you got the result. You can double check if I make some mistake. Okay, thank you.